Welcome everyone to webinar number 12 of Quantum London. It's been a long journey. It's unbelievable. We are already at number 12. And today we have another exciting talk. It's going to be about the first commercially available quantum computer in the UK. So be ready for that. For everyone who's new, just a couple of words about Quantum London. We are a community of people very curious and about the business implications of quantum computing and quantum technologies. So we build a community of people who share this interest. So there will be the chance to ask questions in the chat on the right-hand side. I see a few people already introducing themselves. Yes, if you want to tell us where you're from, this is also an international community, which is great. And for the speakers tonight, we have M.Paini from Rigetti and Alexei Kondratyev from Standard Chartered Bank. As I was mentioning 1 second ago, they are working as part of a consortium which is building the first commercially available quantum computer in the UK. So they will tell us everything about what it is, where they are with the implementation, and most importantly, why this is important for the ecosystem. Together with me, you see Paolo. He is the co-founder of Quantum London, and we will be moderating questions. Normally, we collect those questions and we leave time to the end to do some Q&A. So myself and Paolo will be looking at those questions and we'll make sure we ask as many as possible to our guests. But without any further ado, I will hand over to Marco and Alexei. They can do their own introduction and lead us through the talk.
Hi, everyone, and thanks, Manuel, and thanks, Paolo, for inviting us. My name is M.Paini, and I work for Rigetti in the UK. I'm currently leading the program that Emmanuel has just mentioned, which I will talk about in a little bit. Leave it to Alex for his introduction, then I'll share my screen and start sharing some slides.
Hello, everyone. I'm Alexei Kondratyev, Head of Data Science and Innovation at Standard Chartered Bank. Together with Rigetti, we participate in a consortium building the first commercially available quantum computer in the UK. And today, I will be talking about one particular use case, which I believe is very interesting and brings us one step closer to demonstrating quantum advantage. Marco, over to you.
Thank you. Okay, so let me do the screen share. And please tell me if you... Okay, yeah.
Oh, we see the entire PowerPoint application, but yeah, perfect.
Okay, perfect. Okay. So two main things we'll cover, and I think we'll leave quite a bit of space for questions. So we'll talk a little bit about first the project overall, and I will do that, and then as Alexei had alluded to, one specific use case. Okay. Now, first things first, quickly. So Rigetti is a full stack quantum computing company. We build all the components from the quantum processors to the software to the development framework that allows programming of quantum computers, and we make the services, so the access and then the ability to program quantum computers available on the cloud. So we cover fundamentally the full stack. The company is based for the most part in California, in Berkeley and Fremont, and we have offices in the UK and in Australia. Okay, just quickly the context of the project. So as part of the Industrial Strategy Challenge Fund, one of the 23 challenges that were created as part of ISCF is a quantum challenge that has gone through, the program has started now, has been around for some years, and it's gone through different waves. We are at present in wave 3, and actually, I believe last week there was even a quantum meetup on the latest sub-wave of wave 3. So we participated at the end of 2019 as a consortium, including Rigetti, UK Standard Charter, but also Oxford Instruments and Phasecraft, which is a UK startup that does quantum simulation software, and the University of Edinburgh. We participated in the competition with a project, which is the one that I will talk about, called Quantum Computing Platform for NISQ-era Commercial Application, where NISQ stands for Noisy Intermediate State Quantum, which is fundamentally how today's quantum computers are defined. So still at an intermediate scale and with some noise, with some errors. We were successful in the competition, and the project started in September of last year, 2020. And it is a 3-year project, so that will continue until August, at the end of August of 2023. Now, a little bit about the project. What is the project? And actually, I'll talk a little bit about also the reasons and how we've come to, defining the proposition. So the first, I think, the original observation that actually led to define the project really started from just a simple observation, which was that the UK quantum ecosystem is particularly active, both at the startup level and at the academic level. But there was one evident gap, which was actually the availability of a physical quantum computer of some size, where some size means the tens of qubits. So the core of our proposition, and it still remains the core of our proposition, was building a quantum computer in the UK, and do that at with speed, and that is leveraging the technology that had been developed by Rigetti in the US over the years. So building a quantum computer is difficult, and is particularly difficult if starting from scratch. So our idea was to try to stand up a quantum computer within a year or so from the start of the project, and again, of a size that is comparable to the largest quantum computers around. Now, we soon realized, let me actually just show a couple of pictures. Unfortunately, we don't have pictures. This is more of a curiosity. I don't have pictures, or I should say, I do have pictures, but they're not good enough yet of what we're building at the moment. So I'll be happy to share the real pictures in a few months. So this is just a view of, say, what quantum computers in a small quantum computing data centers look like. This is for the ones that might just be curious about, wondering what a small quantum computing data center looks like. So quantum computers are contained in those cylinders, and the stuff that is connected to it is all the classical systems that control them. Now, again, as a curiosity for the ones who haven't really seen the inside and wonder what it looks like. So this is what's in those cylinders. And actually, the true quantum computer is just that tiny little disk here at the bottom. That is, and maybe I should even say, the core of that is something that is under the center of the disk here. And that is truly the QPU, the quantum processing unit. So this is an old QPU that was fabricated by Rigetti, and again, we fabricate pretty much the QPU, and we assemble all of the components. So all of these things that you see here that make it look very complicated, they are all fundamentally control systems. Now, not all quantum computers look like this, by the way. Just as a note, this is what Rigetti, IBM's, and Google's, for example, for the most part, they look very similar, and this is what they look like. Now, there are others that, on different technologies that look quite different. Now, again, we have at Oxford Instruments, where the quantum computer is being built now, we have a fridge that is undergoing final test that looks very much like the picture that I've shown you from Berkeley. But the rest isn't ready yet, so I'll be happy to share proper pictures as soon as they're ready. Now, when we thought of this idea of deploying a quantum computer, we soon realized that just deploying hardware wasn't sufficient to trying to create commercial value. And as we were thinking through this, I think obviously the first thing that comes to mind is that is also necessary is applications. And it's almost, by definition, it's almost obvious given that there's nothing you do without applications. And even that isn't sufficient because you need then the consumers of those applications. So you need end users. And so we refined the original definition of the scope by thinking, by including these elements and actually thinking about which applications and what sort of engagements we wanted to try to build. And when it comes to applications, I think there are two types, both important. One is at the level of error mitigation and quantum verification. So all of those things that actually support the present quantum computers that have still need quite a bit of support. And again, that is because of the presence of noise and errors. And even because of our inability in principle to even be able to say whether a quantum computer that is large enough has made correct computation or not. And that's, so that's quantum verification. And then there's the other set of applications, which are actually the applications that are for the use of end users. And so in particular, industry applications, and, the spectrum goes all the way from financial services to energy and pharmas, et cetera. So we wanted to build a program that integrated all things, and not only because they're all important aspects, but also because there's some sort of, there are benefits. So the work on each feed in to the other work streams. So in other terms, by working with real hardware and having application teams testing on real hardware, you actually realize and feedback requirements. You realize what things work and what things don't work as well, and you feed requirements back into hardware teams, and then vice versa. By doing work on applications and specific class of algorithms, you realize which things are actually possibly more useful for specific industry applications. As again, in some cases, that isn't necessarily intuitive. So the final, I suppose, the final thing that we wanted to put together was, if this was the vision, was making sure that actually first we picked the right set of applications, but also we had the right team to be able to deliver on that vision. And so, and I haven't said it clearly, sorry, Rigetti is the lead in this consortium, and we started originally in defining, making this exercise around defining what was possible interesting scope. And so Oxford Instruments has been leader globally in cryogenics for some time. They had an interest in growing in quantum computing specifically. And so that, when it came to the dilution fridges, which are needed by quantum not we decided to partner with Oxford Instruments. We hadn't done it in the past. So in Berkeley, we've not been using to date Oxford Instruments technology. So that is a different setup from what we have in California. And not only that, I think we've, Oxford Instruments also, demonstrated interest in possibly looking at, offering a quantum computing as a service offering. And so Oxford Instruments not only is providing the dilution fridge, but they're also providing the hosting facility and hosting services. So right now the system is being built at Oxford Instruments premises. And then when we thought of applications, there are, I think, there are two areas that are right now considered as key applications for end users. One is simulation of physical systems, also known as quantum simulation with, so molecular chemistry or solid state simulation. Applications are for science, material science, for drug design, and etc. And Phasecraft is a small startup based in the UK, funded by academics, a professor from Bristol University and two professors from UCL. And they really represent excellence in the space. And so we've set up a quantum simulation work package with Phasecraft to explore quantum applications applied to simulation of physical systems. Now, the other area is again considered as one of the most promising near-term areas for quantum computer is quantum machine learning. The University of Edinburgh had done some really interesting work around some aspects of quantum machine learning. And with Standard Chartered and with Alexei, we had already collaborated and had several conversations in the past on specifically in one area, which was generative models and the use of quantum computers for generative models. And so this is how we started shaping this idea of exploring quantum machine learning applications applied specifically to finance. Now, finally, as I was saying, there's another class of applications quite different, which is applications that are for the, to support the early quantum technology or today's quantum technology. And so the University of Edinburgh has also been, at the forefront of research in the so-called quantum verification. So quantum verification, again, consists in finding efficient protocols to verify the computations of a quantum computers. This is far from obvious, and the reason is because we want quantum computers, in fact, to do computations that cannot be done classically. That's the whole point. Now, that raises, of course, the question of how do we verify that that quantum computer did the result of the quantum computer produced is correct or correct within some bound. And so that is the entire field of quantum verification, coming up with things that are efficient enough to be able to be done classically that give us an indication of the correctness of a result. I have to say, if quantum verification was the original scope of this work package with the University of Edinburgh, we have expanded this now, and we are actually dedicating more attention to another thing, which is error mitigation or quantum error mitigation, which is the study of protocols that instead mitigate the effects of noise and errors in today's processors. So both things are really important, and there is a great deal of research that is ongoing on error mitigation. And it is key, together with quantum verification, to be able to get to the point of first making a computation that is good on a quantum computer, and also we can certify that it is good and it is at a level that classically cannot be done. That's the whole point. We have also thought a little bit about the engagement with the broader community. For now, we are focusing really on laying the foundations of the program, so building really the hardware and the initial demonstrators of these quantum applications. We'll soon get to focus a bit more, in fact, on engaging with the broader ecosystem. And in terms, I suppose, of where we are today, and let me just move on to this slide. It's very similar, but it's got a summary of the deliverables. In terms of where we are today, I think the objectives are, so the facility in Oxford Instruments is almost completely built. And so is, the fridge is also completely built. It's going through final testing, and it's soon going to be, in fact, as early as possibly next week or maybe the one after, through acceptance test. We are producing and starting to work on various components that will be shipped from the US to the UK. And that is because the core, in particular, the QPU, still needs to be fabricated in the US. We have hired the team in the UK, and in fact, they will all be starting in the next 2 months or so. And from, I would say, May, the activities in the UK will intensify. The physical build activities in the UK will intensify, and will try to get the system up and running towards the end of this year. This will be a first system. We're planning to upgrade towards the end of next year to a larger system, trying to keep up with, in fact, the roadmap that we have set overall as a company. So we are still targeting to have by the end of next year a system with more than 100 qubits live in the UK. That is still the key deliverable, having a 100+ qubit system live in the UK. And together with that, we've got a few more that can really be summarized in 5 things in total. And they're all relatively ambitious, depending on how far we'll be able to manage to push these and results, in particular when it comes to results of quantum machine learning and in quantum simulation and in quantum verification and error mitigation techniques. As an example of some of the stuff that we are doing on one of these work packages, I will hand it over to Alexei, who will talk a little bit about quantum machine learning specifically. This is really just an example of the work packages that we are overall doing as a program.
Thank you, Marco. Let me try to share my screen. Hopefully you can see it. Please let me know if you're on the screen.
Yep.
As Marco said, quantum machine learning is probably one of the very few areas of quantum computing where we have a realistic chance to observe some first signs of quantum advantage on the NISQ processors. Specifically, we can look at generative models. We can use parameterized quantum circuits to generate new samples from the learned probability distribution, or we can train a parameterized quantum circuit as a quantum neural network that works as a classifier. So on this page, we have a schematic representation of a binary classifier. It's very new type of research. I believe the first quantum neural network was proposed only several years ago in a paper by Fari and Nevin from Google. And the idea is that if you look at the quantum circuit, where we have a number of quantum registers and 1 qubit and 2 qubit quantum gates operating on these quantum registers, then the circuit looks very much as a network. Obviously, neural network is a little bit of overwrong term. Quantum neural network is even further from real neural network in comparison to classical neural network, but because the end result is a classifier or a generative model, we use the same terminology. So it's a little bit of an abuse of terminology, but nevertheless is more or less generally accepted now. So how it works? We start with a sample, as always in supervised machine learning case. We have a data set of samples. Each sample has a number of features or attributes, and then the sample is being processed by the network. It can be like a black box, and inside this black box we can have different models. Classically we can build a neural network, or we can build a random forest, or we can build some other types of classifiers, say support vector machine and so on. But given a sample, we process the sample through the network, and then we have an output. In the case of a quantum neural network, the sample will be processed by applying a sequence of 1 qubit and 2 qubit quantum gates. These gates can be fixed, for example, control not or control Z or swap gates, or they can be adjustable gates. for example, rotations around x-axis, y-axis, z-axis by some angle, in the case of 1-qubit gates. And then finally, we would have the measurement operator that would give us the answer. If we have just one measurement operator, then effectively we build a binary classifier. So the output would be the 0 or 1. We have 2 class labels. But we can have several measurement operators in the last layer of the network, and then we can have a multi-class classifier. So the question is, first, how to encode a classical data set in the quantum state, which is the input into a quantum neural network. And second question is how to train this network. So classically, neural networks are trained with, say, a backpropagation of error using a gradient descent method. Or we can use some other techniques to find an optimal configuration of network parameters. Classically, we would have network weights and biases, and we would try to find the optimal configurations of weights and biases that will give us the best possible classification results. So the question is how to do it quantumly on the quantum circuit. Before we look at the answers to these two questions, let's first recognize the fact that we are working with the NISQ quantum processors, which are relatively small. So we operate on several tens of qubits. Noisy. So our quantum gates are not perfect. It means that we should probably not have too many of quantum gates in our circuit. Otherwise, the total noise would be overwhelming. And very importantly, the connectivity is quite limited. On this page, we see a schematic representation of Rigetti's Aspen system, where qubits are essentially connected only to their nearest neighbors. And moreover, they're mainly connected in a linear kind of fashion. So most qubits are just connected to one qubit to the left and one qubit to the right. Only a handful of qubits have 3 connections. So they form a bridge between several islands of linear connectivity. However, even this relatively simple graph is capable of building reasonably powerful quantum tree networks, which we can see on this page. So with just 8 quantum registers and using a relatively small alphabet of quantum gates, we can build a network that resembles a tree network. So, for example, qubits Q1 and 2 are connected, and qubits 3 and 4 are connected directly, and then we would connect first 2 qubits with second 2 qubits, and so on. And then we would put as a measurement operator on the final qubit. So 2 qubit gates are here to realize the entanglement. So the qubits are correlated and information is shared. And 1 qubit gates are adjustable gates. 2 qubit gates can also be adjustable. They don't have to be fixed. But for the sake of simplicity and to make sure that the network is not too complex, we usually leave 2 qubit gates as fixed and only adjust parameters of single qubit gates. Now, let's start with the first question. How do we encode classical data into quantum state, which is the input into quantum neural network? Let's have a look at the canonical representation of a qubit state, which is a point on the Bloch sphere, which is a unit sphere. Quantumly, we can look at state of a qubit as a unit vector in the 2-dimensional complex vector space. Looking at the block sphere representation of a qubit, we see that a point on the sphere can be uniquely determined by two variables, two angles, theta and phi. Theta is defined on interval 0 pi, and phi is defined on interval 0 to pi. It means that a single qubit has a possibility of encoding two continuous variables, which is essentially extremely powerful observation. If you would think about a classical situation, a single classical bit can encode only a single binary number, is a 0 or 1. But quantumly, a state of a qubit can encode two continuous variables. So enormous amount of information can be stored in a state of a qubit. After measurement, we can only extract one bit of information. So we can choose particular computational basis and before measurement, and then the end result would be either 0 or 1 in the chosen computational basis. But when we perform operations on a qubit, when we apply quantum logic gates to the qubit state, we operate on essentially a very complex object, a state that encodes two continuous variables. And we are using this fact to encode classical data into quantum state, into quantum registers. So let's look at our graph, which is a tree network specified on 8 quantum registers, on 8 qubits. First, we would look at a data set with some number of features, and we can encode first 8 features as rotations around x-axis applied to the corresponding quantum registers. So we would take feature number 1. We would look at the value of this feature. We would then map a value of this feature, some continuous variable, into an angle, rotation angle on interval 0 pi, and then we would apply rotation around x-axis to the first qubit. Then we do the same with the second qubit. So second feature would be encoded as a rotation angle applied to the second quantum register, and so on. In this way, we can encode first 8 features which can be continuous variables as rotations around x-axis. And then we can do the same with the second 8 features, second set of 8 features, where we would encode feature values into rotation angles around y-axis, also defined on interval 0 pi. So a relatively simple quantum neural network with just 8 quantum registers is able to support a data set or operate on a data set consisting of up to 16 continuous features, which is an enormously powerful result in its own right. So let's look at one particular example which can be implemented and realized on the proposed quantum neural network, and look at the results. The use case here is a well-known data set from UCI machine learning repository. This is Australian credit approval data set, so very relevant from a finance perspective. The data set consists of 690 samples, so reasonably large, but still relatively small, such that many classical classifiers would struggle to learn the underlying distribution. The data set has 14 features and a binary class label 01, which corresponds to credit application being either accepted or rejected. And 14 features would represent various attributes of a predator. From a machine learning perspective, it doesn't matter what these attributes are. We just take them as inputs. The features are actually a combination of binary, integer, and continuous features. So it's a very rich data set. And we're applying our proposed encoding scheme. So first 8 features would be encoded into rotation angles around x-axis, and the last 6 features will be encoded as rotation angles around y-axis. So every single sample in the data set would be encoded as essentially a vector of rotation angles. And then the network is organized in the following way. It's a tree network, as specified before, where we choose control Z as 2-qubit gates that create entanglement. Control Z are native 2-qubit gates on Rigetti's chip. So it's a hardware-friendly implementation. And we have 1-qubit gates such as Rx and Ry, rotations around x-axis, rotations around y-axis, by adjustable angles. So here we have in total 7 fixed 2-qubit gates creating entanglement, and 15 1-qubit gates with adjustable parameters. And the task is to train this network, find such combination, such configuration of rotation angles theta that the measurement on a given sample will give us the correct answer as frequently as possible. There are several techniques how a quantum neural network can be trained. We can apply traditional gradient-based optimization, very similar in nature to what we would do with classical neural networks. Classically, we have a task of finding an optimal configuration of weights and biases. And we can, and the training process would consist in calculating the gradient and then adjusting the network weights in the direction suggested by the gradient. We would calculate first derivatives of our cost function with respect to every individual weight, and then we would apply a small update at each iteration. Would apply a small update to network weights, which is controlled by the learning rate. So that's how gradient-based optimization works classically. And the same can be done here quantumly. We can do the same with where we would apply updates to rotation angles theta. However, there are other methods which in some cases work better. Gradient-based optimization works well when we have a relatively simple cost function. Cost function which is not heavily nonlinear without too many spikes. But once the cost function becomes strongly nonlinear, gradient-based optimization may lead to finding some local minimum, and then we would be trapped in this local minimum, and we would struggle to find a global minimum of our objective function. So other methods, such as evolutionary search heuristics, particle swarm optimization, or genetic algorithm, can be used to find true global minimum, or at least getting very close to true global minimum, which may work better in some cases. And that's what we did. We applied particle swarm optimization algorithm, relatively simple evolutionary search heuristics that searches, very efficiently searches the space of possible solutions. And for this particular data set, we found an optimal configuration of rotation angles. Here we actually used a quantum simulator. So results presented on this page are results from a quantum simulator, not actual quantum hardware. So these experiments are still ahead of us. But on the quantum simulator, which is a perfect quantum computer, we can find an optimal configuration of rotation angles, adjustable angles. And then we can look at in-sample and out-of-sample results as we would do with any classical classifier. In this case, we split the whole data set, 690 samples, into training data set and test data set, equally 50-50. The model is trained on the training data set, and then we also observe performance out of sample on the testing data set. What is very interesting is that the quantum neural network has almost the same performance on the training data set and testing data set. So very little overfitting is happening, which we will talk about in a minute, why this is the case. And also comparison with classical classifiers shows that relatively simple quantum neural network, tree network that we proposed, actually delivers reasonably good results. Here we have a QNN classifier that achieves average F1 score between class 0 and class 1 of 0.85, which is in the middle of the range of F1 scores observed for optimized classical classifiers. And here we have most widely used classical classifiers. We have logistic regression, we have random forest, we have a neural network, multi-layer perceptron classifier, and we have a support vector classifier. So QNN classifier achieves results right in the middle of the range, which is a very solid result because essentially we haven't played at all with the network configuration. We proposed a tree network, and we haven't even attempted to try a different configuration of two qubit fixed gates. For example, we can add more 2 qubit gates to improve entanglement, or we can have another layer of 1 qubit gates giving us more control over rotation, so we would construct more complex quantum state on which measurement will be performed. So without essentially any optimization going into QNN, we have quite a decent result. It also means that there is a scope for improving these results. For example, quantum neural network can be constructed in many different ways, and we can have a collection of slightly different quantum neural networks with slightly different configurations of 1 qubit and 2 qubit gates. And then we would apply a traditional boosting approach where different quantum neural networks, slightly different quantum neural networks would perform classification, and then we can combine these weak classifiers into a single strong classifier with, say, majority voting approach or some other way. But what is very interesting is how QNN results compare against classical neural networks such as multi-layer perceptron. I mentioned that QNN achieves a very good result in terms of regularization, so we don't see big difference between performance on the training data set and the testing data set. So F1 score is actually the same in sample and out of sample, which implies very strong regularization, a very desirable property for neural networks. Classically, simple feed-forward neural network, such as multi-layer perceptron, has a parameter that controls degree of regularization, and regularization is achieved by introducing a penalty term to the cost function. Traditionally, we tend to apply L2 regularization penalty, but it can be L1 regularization penalty or some other kind of penalty added to the cost function that would force some of the network weights to become smaller, or in some cases even zero. In the case of L2 regularization, parameter alpha forces network weights to become progressively smaller. So the larger value of parameter alpha, regularization parameter, ensures that network weights becomes smaller, and it also means that network becomes more linear in a way. And degree of regularization can be estimated by calculating the so-called Lipschitz constant. Lipschitz constant is something that reflects by how much the matrix of network weights would stretch the input vector, the signal. When Lipschitz constant is very large, it means that the input can potentially be stretched a lot. So it implies a very strong nonlinearity in the network. And it is responsible for the fact that for small values of regularization parameter alpha, we observe very different performance in sample and out of sample. So in sample, we have perfect classification, but out of sample classification is substandard. As we start increasing alpha, Lipschitz constant goes down, and performance in sample declines, but performance out of sample improves. So we introduce more and more of regularization, and overall network performance improves. At some point, we reach the best possible outcome. In this particular case, for this particular data set and particular configuration of classical neural network, multi-layer perceptron, the best result is achieved with alpha equal to 40, where performance in sample and out of sample are the same, and actually the same as quantum neural network. However, this point is unstable. Increasing alpha even slightly leads to complete collapse in the classical classifier. So the classical classifier stops learning and stops producing reasonable predictions. It is also reflected in the fact that Lipschitz constant drops several orders of magnitude with a small increase in alpha. When alpha goes from 40 to 50, the network stops working, which is a very undesirable property. It also means that when we work with classical neural network, regularization is hard to achieve. It's very hard to find an optimal configuration of hyperparameters for the network, and the network may systematically underperform. But quantumly, due to the fact that a quantum neural network can be represented as a unitary operator, essentially the whole quantum circuit can be mathematically described as a single unitary operator, linear unitary operator, with a Lipschitz constant being by construction equal to 1. And such a linear system, such a linear operator would always lead to very stable results and would always deliver strong regularizations. So the next step in our research would be to conduct experiments on actual quantum hardware. So that's the next step. And then over time, we would expand and build networks on larger and larger systems. And at some point, when a number of qubits increases, we would reach the point where the quantum neural network can no longer be adequately simulated by the corresponding classical system. So this is a point when we would probably see first tangible real signs of quantum advantage. But even here on this relatively small data set with a relatively small network, we already see some serious positive features achievable with quantum neural network. Potential ways in which quantum neural network would outperform classical counterparts. So I'd like to stop here.
Jump in. I know there's a lot of questions.
Yes, so, a lot of questions.
Perfect. Well, let me ask a couple of those questions, and then M can ask some of the others. So, one of the questions the audience asked was around when Standard Chartered Bank first started looking at this topic and how you engaged senior management on it. It would be useful to know that.
Standard Chartered started quantum computing program several years ago, about 4 years ago. We started experiments on D-Wave quantum annealer. It was our first project where we had the chance to get some taste of quantum computing, learn some basics, and conducted some research on actual quantum hardware, published papers, presented our results. And after that, we decided that we have to be more serious, more systematic in our quantum computing research. We understand that quantum computing is extremely powerful. It's new technology that is going to change everything around us. Because quantum computing, once fully available, will ensure that we have essentially unlimited computing power, in some cases also very cheap. It means that all business processes will have to adjust. The way that the business will adjust. Things which are not possible now will become possible. And we have to be involved in this. From the bank perspective, and I think it applies not only to our firm, but also to any other financial institution, we have to build institutional knowledge of quantum computing. We have to build institutional knowledge of this new technology, such that we have a workforce ready for using this new technology once it becomes fully available, mainstream. And that's why we're also now looking at gate model quantum computing, and we partner with Rigetti and other partners in our consortium on building the first commercially available full stack quantum computer in the UK. I think for us it's a very natural process. It started as a relatively small initiative, almost like a proof of concept, and now it's a proper systematic approach with full support from our management.
Location and ownership of quantum computers. So do you envisage a world where every bank will have its own quantum computer somewhere close to the trading exchange? Or do you think quantum computing as a service is the way to go forever?
Well, I don't know. I don't know. Who knows? Maybe the winning technology will be completely different from what we have now. We experiment with superconducting qubits. There are, as Marco mentioned, there are also photonics, trapped ions, neutral atoms. There are many competing technologies. Nobody knows which technology will be the winning long term. And who knows, maybe quantum computers over time will become small, portable. But right now, I think the way we look at quantum computing, we stick with superconducting technology. I think cloud access to quantum hardware is the way forward. That's what we're doing now. And I think our consortium is probably like a real testament of our intention. So we look at superconducting technology, and we believe that cloud access is the way forward.
Slight variation on the same topic, and by the way, it's great to see the community at play in the chat, because a lot of the questions have been answered already. But the question was, if the quantum computers are available as a service, what is the key driver of building one in the UK? The key driver or the key drivers?
I think there are two different levels. One is a more technical one, and so I think in that case it is the same play as cloud solutions in a way. If you look at major cloud providers, they have a global solution with local deployments, and main reasons for that are data privacy, maybe not too much of a worry now for quantum computing, but data privacy and performances. So performances for a quantum computer, there are reasons. So there are things where actually latency matters, especially when it comes to the execution of some circuits that have, that run on multiple iterations, so variational algorithms. So I suppose it's very similar to, you could think of it as very similar to, classical cloud solutions. That's, I would say, those are technical reasons. Then the other one, I think more important, even from the perspective of what maybe Innovate UK intends to do, is the local development of skills and the ecosystem. So it isn't just, I suppose, the work that is being done by the consortium, and even that counts. The level of access, even just now, of the partners of the consortium to the system is giving pretty interesting results. We've seen it on generative models. We've seen it with Facecraft on some stuff on quantum simulation. Already now, I think that would make a difference. But the other one is the level of conversation with local partners already at this stage, even if the system isn't up and running yet. As increased significantly. Probably we wouldn't have had this level of conversation if it was just a system in the US. And now, even in the recent round of feasibility studies, we've locally been discussing and working on proposals with local startups, etc. So I suppose that the non-technical is that I think it really stimulates the development of the ecosystem and actually skills, because we'll have a team that will be developing skills on assembling a quantum computer and so on and so forth.
From the chart, which is, how do you prepare for the talent needed for the future? That's what we want to think about. Also, from Standard Chartered, Alexei, you said, you are looking at, building your position on quantum. So how do you prepare for talent for the future?
I think banks are in quite fortunate situations, and I'm talking about all kinds of large international banks like Standard Chartered. We tend to have large teams of quants or quantitative analysts, quantitative researchers with a very solid background in quantitative subjects, usually in physics, computer science, mathematics. So we have a lot of people who are familiar with high-performance computing, with quantitative methods, and many have actually degrees and PhD degrees in physics. So we have a natural pool of talent who might be ideally suited for picking up the knowledge of quantum computing. And I think that's how historically banks started to get involved in the quantum computing. It's probably former physicists decided that it's time to actually try this new technology and see if it would help to expand this the range of tools, our toolkit for all kinds of financial modelings that we are doing in banks. So I think banks are quite different. Probably not many other types of corporates or companies, financial institutions would have such a kind of workforce which are already partially trained or very suitable to be educated in quantum computing. Probably technology companies with hundreds, if not thousands, of computer scientists are also naturally positioned for quantum computing age. I think the fact that Google is building their own quantum hardware is a testament to this. And we know that Amazon and Microsoft are deeply involved. Intel is obviously also involved in this. But banks have the advantage of having modelers, a deep pool of people with degrees in physics, mathematics, and computer sciences, and people who know how to do modeling and translate different types of use cases into mathematical models. So that's why I think banks, large banks that have quantitative research departments are at the cutting edge of quantum computing research as well.
Oh, unfortunately, on the presentation. So I would like to thank you, Alexei and Marco, for their talk. Super exciting space, and also Alexei, I might have a slightly better understanding on how you do machine learning with quantum computing. Thank you for that. But it was a long way for many of us here in the community. So thank you very much, and. Also from Paolo and Anahita, unfortunately, we didn't have time to give you an overview of what's coming. That was in the chat. But yeah, thanks a lot again, and looking forward to the next event. Thanks again, Marco and Alexei. Thank you.
Thank you very much.
Thanks very much. Thank you.